Okay, so welcome to this short video. In this video, we will discuss about the bonding and so on. We know different types of materials exist. For example, we have metals, um, polymers, uh, ceramics, and so on. So all these different materials are classified on the basis of the type of the bonding. So the bonding plays a very important role in these materials. For example, metals, the predominant bonding is the metallic bonding. In polymers, you have covalent bonding mostly, and ceramics you could have ionic or covalent bonding, okay, depending upon the material. So the bonding actually determines the what type of material system it is, and uh, and therefore it is very much important to understand what is a bonding uh, uh, in these material systems. And typically you can model this bonding in a very simple way as two atoms connected by means of a spring. Okay, so the two atoms are bonded in this case by means of by using a spring, and the spring will have a stiffness. Any spring will have a stiffness. Stiffness means resistance to deformation, elastic deformation. So when you apply a load, there will be always a resistance for this spring against that deformation. So that is what is known by the name stiffness. So the objective here is to determine the stiffness of this of the bond present in these material systems from the potential well diagram. So to start with, we have to know what is the potential energy between the two atoms, and the potential energy, which if I use the symbol U, is the sum of the two terms, which is attraction energy and the repulsion energy. So you have two terms. So when you bring two atoms together from far away distances, what happens is that initially there could be an attraction, and when it becomes too close there could be a repulsion. So I will not go into the details of what is attraction energy and repulsion energy. That will be covered in a regular classroom, but uh, but the potential energy you can in general represent in this form: minus of a by r power m plus b by r power n. And here a and b are constants. Okay, a and b are some constants depending upon the type of the bonding it is, and m and n are also the exponents, which are again constants, okay, which again depends upon the type of the bonding. And typically the value of m is less than n, and much less than n. For example, in case of ionic bonding, if I write ionic bonding, m will be typically, m is of order 1 and n is might be in a range. Again depends upon the type of the material system involved. It can be something like 7 to 12 or 10 to 12 or something. So it's a much larger number. N is much larger number when compared to m. So this is an important point. And because of these features, if you draw the potential well diagram, it looks something like this. So potential well diagram looks like this. So it is drawn with U along the potential energy along the y-axis, and the interatomic separation distance, R is the separation distance, interatomic separation distance. Okay, and if you make a plot of this, it looks like a well. So here is that well. Okay, so well, and you can see that there is some one particular energy level where the energy is minimum. So this is the U minimum region. The potential energy is minimum, and correspondingly there is a separation distance. So this separation distance, okay, this separation distance, and that we call it as the equilibrium separation system distance. So R0 is the equilibrium separation distance. So equilibrium separation distance corresponds to the separation distance, or the distance of separation between the two atoms when the energy is minimum. So this is my equilibrium separation distance. So when you apply some force into it, the two atoms have a tendency to come back to this equilibrium separation distance, it's very similar to that of a spring. When you stretch it, when you take a spring and stretch it, it has a tendency, there will be a restoring force acting on it, which will pull back the spring to the bring back the spring to the original position. Okay, so very similar to that, there is actually a restoring force acting on it also. So you can actually find out what is the force. So how would you determine the force? The force, you get it from differentiating the potential energy. So force is nothing but differential of potential energy. So now if I draw potential energy with respect to separation distance, it looks something like this. And now corresponding force to distance, if I draw, you get it by the differentiating the UR diagram. And you can see that initially if you see this part, if I use some other color, if this part of the potential well diagram, you can see that the slope, if I take the slope is nothing but the force here. The slope is negative, so it starts with the negative slope, and it keeps on increasing. So right, so this is something like this. So up to here, so it is a negative slope, and once you reach this point, the force, the potential energy is minimum. So it's a minimum potential energy region, so the differential of this one should be equal to 0. So this is actually 0, so force is 0. So the important point here is a force at r equal to r0 is nothing but du by dr at r equal to r0, and that is actually 0. So the force is 0, which means that the system is under equilibrium. There is no net force acting on the between the two atoms at equilibrium. Okay, so since there is no net force, so it will be in a very stable situation. And once you go further from towards the right of this equilibrium separation distance, so this is my r0. Okay, what happens is the slope is positive here, and you can see that the slope is positive for the further in their regime. But what you will see is that the force is positive, and it keeps on increasing up to certain distance, and after that there is an inflection happening, so the slope is decreasing with respect to distance. Okay, so it can be considered as an inflection point, for instance, and then it actually comes down. Okay, and this is my maximum force. Okay, so this corresponds to the maximum force, and there can be a corresponding distance also, which can be considered as a dissociation or separating distance or something like that, dissociation distance. Okay, so this is what which is going to happen. So important point here is the force is a 0 at the equilibrium separation distance. Okay, now once you know the force, our objective is to find out what is the stiffness of the spring. So from the force you can find out the stiffness. How will you find out the stiffness? Because we know from from mechanical behavior of materials, for instance, or example, if I take a material rod like this and subject it to some force, okay, uh, within the elastic limit. Okay, so within the elastic limit, there will be some displacement happening to the body, right? So there will be some displacement happening to the body, and if you make a plot of the force to displacement, I will use here r, just so that I can compare this with the interatomic separation distance. So this is nothing but the displacement, force along the y-axis and displacement along the x-axis. You get a plot within the elastic limit, especially for something like metals or ceramics, or in case of ionic materials. So what happens is that initially it is a linear regime, and this is how the force to displacement curve looks like. And if I differentiate this plot, that is df by dr, and then we get what is called as the stiffness. Okay, so this is what is known as the stiffness of the material. So the stiffness is the resistance to deformation within the elastic limit. So their regime is within the elastic limit, and if I take the slope of the force to displacement curve, and I will get the difference. get the stiffness. So we already have seen that that the force is nothing but the du by dr, and therefore the stiffness is df by dr, and therefore this should be d square u by dr square. So the stiffness is something which is corresponding to that of the curvature of the diagram. Okay, so of the potential well diagram. So because this is corresponding to the square of the potential energy with respect to distance, so it is corresponding to the curvature of the potential energy diagram at r equal to r0. Okay, so if you see here, so this is my potential well diagram, and depending upon what is the curvature here, um, uh, your stiffness of the material will change. Okay, and this is nothing but the potential well diagram. Okay, now the point is to determine the stiffness with the understanding that this is my potential energy, and this is a very general equation for potential energy. It could vary depending upon the type of the bonding. So u is, if I use the general equation, minus of a by r power m plus b by r power n, and I can calculate force by differentiating this u with respect to r. Okay, and in that case it becomes equal to minus m a r power m plus 1 minus, this becomes r power minus n, so the differential of this is minus n b by r power n plus 1. And at r equal to r0, if I take r equal to r0, which means at the equilibrium separation distance, then at r equal to r0, this everything becomes equal to r0, and then in that position, the force is actually 0. So my objective is to write b in terms of a. So if I write b in terms of a, so this is minus of ma by r0 power m plus 1 is equal to, and this should be plus. Okay, sorry, this is plus because this is minus m, so that should become, this term should become plus. So my if I bring this term to the right hand side, this becomes nb by r0 n plus 1. So if I write, solve it, so I get b is equal to, I think, r0 n minus m into m by n multiplied by a. So this is what is b, and I have written b in terms of a. Okay, so my objective is to differentiate further and find out what is stiffness, because we define stiffness S as df by dr at r equal to r0, but yeah, so so if I differentiate this df by differentiate this force again with respect to distance, so this becomes S is equal to, I'm differentiating this equation. Okay, m minus of m plus 1, so it becomes minus that term, so minus of m into m plus 1 a, and stiffness at r equal to r0, so I am putting this as r0 m plus 2, and similarly the other next term, second term, is this becomes minus, so minus of minus is plus, n into n plus 1 b by r0 m plus 2, n plus 2. Okay, so this is the equation for the stiffness in a very generic case. Now we can substitute for b, so because we know what is exactly b here, b is this term, so if I substitute for b there, so this becomes m minus of m into m plus 1 into a divided by r0 power m plus 2 plus n into n plus 1 by r0 power n plus 2, and b is m by n, okay, m by n r0 power n minus m, and multiplied by a. So a is a common factor here, you can take it outside, uh, and you can see that this n and n gets cancelled, and this term, if you see this and this, sorry, this and this one, this is r0 n power r0 power n minus m divided by r0 power n plus 2. This is nothing but 1 by r0 power m plus 2, because n and n gets cancelled, and you get something like that. So r0 power m plus 2 is also a constant, so if I take that also outside, so r0 power m plus 2 is common there, right? It's not a constant, it's common in both the terms. Okay, so I'm taking this outside, and what is left is in this first term it is minus of m into m plus 1, and in the second term it is m into n plus 1. Okay, so now this becomes 1 minus m minus m square minus m, right? This becomes minus m square minus m, and this becomes mn plus m, and m and minus m got cancelled, and you get m into n minus n. Okay, so m into n minus n. So that is the term which you get. So the stiffness is equal to a by r0 power m plus 2 m into n minus m. Okay, m into n minus m. Remember, m and n are exponents. M corresponds to that of the exponent in the attractive term of the potential energy, and n corresponds to the exponent in the repulsion term in the potential energy, and n is greater than m. Okay, and if you consider an ionic ceramic where the attraction is basically in case of ionic ceramics, I'm taking an example. It need not be always ionic, you can consider any example, but ionic is little easy because the attraction energy is nothing but the Coulombic attraction. So the Coulombic attraction is q1 q2 by 4 pi epsilon 0. This is my a into r. Okay, so I'm with the negative sign. So this is my attraction energy, and if you see this term, this is nothing but my a here. So you can, if you want, you can actually substitute. Q1 and Q2 are the charges. In case of for example sodium chloride, it would be plus 1 and plus 1 E, and Q2 will be minus 1 E. Q1 corresponds to, Q sodium and Q chloride ion, and sodium corresponds to plus 1 E. E is the charge of the electron. We can multiply it. You can use this value 1.6 into 10 power minus 19 coulombs, and epsilon 0 is the permittivity in vacuum, which has got its own value. I forgot the value, so you can substitute the constants here. Okay, so you can substitute all these values, and at r equal to r0, this becomes equal to r0. So this is the attraction term, and this corresponds to my a here. So if you want, you can actually substitute it. But the important point is here r0 power 1. Okay, r0 power 1. So m is actually 1 in case of ionic ceramics, and n, as I told, can take any value, might be from 8 to 12. So if I take something like 8, assuming n as 8. Okay, and what is the repulsion energy here? So the repulsion energy is in case of ionic ceramics is b by r power n. It is because of the Pauli's repulsion. So when you bring the two atoms, ions together much closer, so what happens is that the ionic cloud of the chlorine starts interfering with the ionic cloud of the sodium, and there will be a repulsion between the very strong repulsion between the two ions at very small distances. Okay, so that is a repulsion, and this we can see from this equation itself. This becomes highly dominant at very small distances because n is much higher when compared to that of the m, and this is a positive energy, or we call it, because it's a repulsion energy, and this comes out to be negative. So I need not have to put negative here, because q1 into q2 is actually negative. Plus 1e into minus 1e should be minus of value, so the minus will be coming out automatically. You do not have to use minus here, but it implies that this is a repulsion energy, and this is actually this is an attract this corresponds to an attraction energy, and this corresponds to repulsion energy. And in case of ionic ceramics, m equal to 1 and n equal to, n can be varying, but depending upon the type of the ceramic. But if you assume n is equal to 8, then I substitute it into this equation. What I will get is s is equal to, I will retain the a, r0 power m plus 1, that m plus 2, right? M plus 2, so m is 1, so this should be 3, and the constant will be, I put m equal to 1 and n equal to 8, so 1 into 8 minus 1, that is 7. So 7a by r0 cubed. Okay, so that is the stiffness. We need not have to bother too much about this. This is actually a constant. So what is important here is that the stiffness comes out to be proportional to 1 by 1 by r0 cube. I have written wrongly. S is equal to 7a by r0 cube, and this is a constant. Okay. A is a constant. And in case of ionic ceramics, a is nothing but this value. You can substitute it, and you multiply by 7 and divide by r0 cube, you will get the stiffness. But the important point here is that the stiffness is proportional to 1 by r0 cube in case of ionic ceramics. Okay, so this is not a universal equation. It varies, because once you change the m, then the relationship between the stiffness and the radius also changes. Okay, now for example, in case of van der Waals forces, which are secondary forces present in many material systems, and this m can be of the order of 6, for instance. And if you have 6, if you follow a similar procedure, you may get with some other relation between s and r0. It may not be always r0 power 3. But one thing you can see is that if you reduce the r0 is nothing but the interatomic separation distance at equilibrium conditions. Equilibrium means when the force is 0. So if I go back, so this is the r0. So if I reduce the r0, so for example, if I bring it closer towards here, and you have a very sharp curvature, then what you will see is that the stiffness of that material will be higher. Okay, so this is all about the relationship between the stiffness and the interatomic separation distance, equilibrium separation distance. And this is quite a useful relationship, and this also shows that the stiffness is an inherent material property. It is strongly related to the type of the bonding which is present in the material system.